Great, thanks. It's a great pleasure to introduce Zheng. He's an assistant professor in ECE at UC San Diego. He got his PhD at Oxford, and he was a postdoc at Harvard and a research associate at Imperial College London as well. He works on control and optimization and applications in several physical systems and autonomous systems. He has got a lot of awards, European PhD thesis award on control for complex systems, for instance. And the work that he's going to talk about today is especially interesting to me and to many of you here, which is an analysis of the optimization landscape, the non-convex optimization landscape for LQG control problems. So yeah, so all yours. Yeah, thanks.
Okay, great. Thanks for the introduction. It's great to be here today. Good morning, everyone. So welcome to my presentation. Today, I'm going to talk about some of our recent work on non-convex optimization for linear quadratic Gaussian control. Let's see. That works. So first of all, I would like to thank my collaborators for this work. So this is a joint work with Professor Yujie Tang at Peking University, Professor Nani at Harvard University, Dr. Yue Sun and Professor Marvin Faze at the University of Washington. And many of the results I'm going to talk about today are taken from the following two papers. So as we all know, in the past few years, we have seen very exciting news about applying model-free method and data-driven control tactics in many applications. And many of them use direct policy update, and they become very popular in both academia and in practice. And indeed, we have seen very successful stories from game playing, robotics, and drones. And in principle, the high-level idea of many model-free methods are indeed very simple to understand. We first apply an initial control strategy to a dynamic system, and then we observe the system output. Based on the observation, we evaluate the control performance. And then we refine the control strategy using some local search algorithms, such as gradient descent. And this idea actually offers us a lot of opportunities. It directly search over a given control policy class, and it also directly optimizes performance on the true system, which allows to bypass the model identification procedure. And however, as you may know, there are also some challenges in terms of building performance guarantees for these iterations, such as convergence, whether this iteration will converge to some point, suboptimality, whether the resulting control policy has guaranteed optimality, and as well as some complexity. So many of these questions are highly non-trivial, even for linear dynamic systems. So in this talk, I'm going to focus on a class of optimal control problem. So this block diagram is a standard figure for feedback control system. So we have a dynamic system. We can observe some system output, and based on the measurement of the system output, we would like to design feedback controller to regulate the system input. And the control theory has become the principal use of feedback loops and algorithms to drive a dynamic system to its desired goal. And in particular, in this talk, I'm going to focus on a class of linear quadratic optimal control problems. So in this case, the system dynamic will be linear, which means the state of the system at the next time step will be a linear function of the system state at the previous time step and the control input plus some noise. And the system output will be a linear function of the system state plus some noise. And we would like to design the control input U1, U2 to minimize the quadratic function in terms of the system trajectory. And this formulation indeed has a lot of practical applications. And if we can directly observe the system state x of t, which means the matrix C is identity or the noise is zero, this problem is known as the linear quadratic regulator, or LQR. If we cannot observe the system state directly, we can only observe some system output. This problem is known as the linear quadratic Gaussian, LQG control. And for both of these two problems, there are very extensive class results, such as dynamic programming, Card equation, which allows to get a optimal control policy for both of them. And one major challenge now is how to perform optimal control when the system is unknown. Because if we like to use dynamic programming or the Card equation, they all need to know the system dynamics, such as A and B and C, in order to solve the problem. And so in this talk, we are going to focus on a class of a model-free method, which use direct policy iteration. So first of all, we consider a parameterization of the control policy. Let's say we use neural network, because neural network has been used a lot in many applications. But actually, for this problem, we don't have to, because control theory has already told us many structural properties. For example, for the LQR problem, if we can directly observe the state, it is known that linear feedback is sufficient. So we only need to design a static matrix K. So K is a matrix. So this will be our design variable. So we can parameterize the optimal policy using a simple matrix K. Once we have a control policy, then we can evaluate the performance by evaluating the closed response. In order to make sure this cost to be finite, we would like to consider the set of stabilized controllers. Basically means the system trajectory will go to 0 or go to some equilibrium point. Then we have finite control cost. And then we can formulate the LQR, or this optimal control problem, as a model-free optimization problem. So this is our cost function, and this is our feasible region, and we want to solve it. And then probably we can apply the direct policy iteration. So we can evaluate the gradient, and then we do gradient descent or its variant. And now we can now do this iteration. Now the problem is that, does this iteration give us some good properties? Does this iteration converge, or do we have a guarantee of this iteration? And luckily for this problem, even though the problem is non-convex, but it has been shown that this problem has some good optimization negative property. For example, this set is non-convex, but it's connected. And this cost function is non-convex, but it's set by a property of a gradient dominance. It's basically like a strictly convex function. And then we use this gradient iteration, we can actually obtain very fast global convergence. So this iteration will converge to the globally optimal solution. And actually, this result is very recent, like just about 5 or 6 years ago. I think Professor Marian Faze will may talk about this result next week. So you may hear more about this direction. So after this work, actually, there's a lot of paper following up, which studied a similar problem or some variant or some modification of the algorithm or some other aspect of this problem. And most of this, and actually all of these results, they require a direct observation of the state. They require state feedback. So in this talk, I'm going to focus on the partially observed LQG case, for which we cannot directly observe the state. And the result for model-free LQG control are much few. There's only a very few papers on this topic right now. Probably the reason maybe the LQG is more complicated than LQR. So first of all, we need to use dynamic controller. We cannot just use stat feedback. So stat feedback is not sufficient to get a good performance. And its non-convex landscape property are much complicated than LQR. And so in this talk, I'm going to focus on non-convex optimization for LQG. In particular, I'm going to introduce some results about the property of the domain. So how does this set of stabilizing controller look like? How does the feed region look like? And then I'm going to talk about some property of the cost function. So we know the cost function is non-convex, but we do not know other properties, such as the structure of the station point. How does the station point look like? And if I have time, I may also talk about how to escape set points for this particular non-convex optimization using perturbed gradient descent. So I'll mainly focus on those first two questions, but I may also talk about the third question if I have time then. So by the way, feel free to ask questions if you are unclear about anything. So just interrupt. Okay. Let's move on. So let's be more precise about the problem setup of LQG formulation. So as I talked about, I focus on a class of linear dynamic system. In this case, I focus on the continuous time domain, but we also have result in the discrete time domain. So for this dynamic system, we would like to design a control input based on the observation to minimize this quadratic cost. And we do not need to use neural network for this case. And the control theory has already told us the optimal control policy will be in this form. It will be a dynamic system. Again, it's not a state feedback, not U equal to K, Y, not this case. So it will be a dynamic system. And in this case, we need to design 3 matrices. So AK, PK, CK will be matrices. And this will be a dynamic system by itself. And say you can consider it to be it will be the internal state of the controller. You can consider it to be the state estimation of X of T. And the dimension of this internal state is called the order of the controller. If the dimension of the internal state is the same as the dimension of the system state, we say the controller to be the full order. And sometimes you can also consider reduced order control design. Maybe the dimension of this is too large. You may consider reduced order control design. But the optimal controller will be full order. People know this. And another important notion in control theory is the so-called minimal controller. Basically, the input-output behavior cannot be replicated by a low-order controller. And this is the same as this pair of matrices are controllable and observable. Basically, these 2 matrices is controllable, and then these 2 matrices are observable. And we will make the standard assumption saying the system is controllable and the system is observable as well. Okay, so if we know everything, if we know the system dynamic, if we know the matrix ABC, know everything, then we know the optimal solution will be a common filter for state estimation plus a LQR feedback based on the estimate state. So basically, this will be the optimal policy. And the parameter K and L can be solved by using 2 Riccati equations. And what's the problem of this procedure? So the problem is that in order to solve this Riccati equation, in order to formulate this particular control policy, we need to know the dynamic explicitly, because they all depend on the dynamic explicitly. And in this talk, I'm going to focus on model 3. So I don't know this A, B, C, and I'm going to focus on a model 3 formulation. So basically, what I will do is that I will combine these 2 dynamic into 1 equation, put them together, then you will have this dynamic evolution. And then we consider the feasible region of the control parameter to be the case this matrix is stable. Basically, you want to make sure all the state converge to 0 or converge to the equilibrium point. Otherwise, your system will blow up and your cost will be infinite. And once we have a controller in this set, once we have a set of controller in this set, then we can evaluate the cost under this particular control policy. And in particular, if we know the model, we can solve the cost analytically. Otherwise, we need to use system trajectory to estimate the cost by solving 2 Riccati equations if we know the system model. So then we can formulate the LQG problem as a non-convex optimization in the following form. So we have a cost, and then we have a control parameter to design. And this control parameter should satisfy a set constraint. Basically, this matrix should be stable, which means the eigenvalue of this matrix should have a negative real part. And actually, this formulation is not new. You can find exact formulation in this paper almost 30 years ago. So people have considered this formulation already, but from different perspective. So now, once we have this formulation, we can start an initial control policy, K0, and then we estimate gradient, and then we do gradient descent, or we do a policy update. And then we perform this loop using the data to perform this iteration. But now the question is, does this iteration converge? Or how does the, if it converges, what does the convergence rate? Or what was the convergence speed? And actually, all these questions right now are open. So I'm not going to talk about this question because I didn't have answers to this question. What I'm going to talk about is some landscape property and some how does the non-convex optimization look like. So what I'm going to talk about is about the connectivity of this set. So is this set connected? Or if not, how many connected components can it have? So people know this non-convex, but people do not know other property before. And then I'm going to talk about the structure of station point. Because if you use a policy update or use gradient descent, at most you can converge to the gradient equal to 0. Because if gradient equal to 0, you look around and you cannot find improving direction, probably you are going to stop there. So then how does this set look like? Are there any spurious strict suboptimal point or something else? And how to check if a station point is globally optimal? Because it's probably non-convex, and we need to find some condition to check whether a station point is a global optimal. It may be locally optimal, locally maximal, or set point. And in the end, if I have time, I'm going to talk about how to escape some bad station point using perturbed gradient descent. So, any questions so far about the problem setup?
So, Yang, so you were saying that you know, whether the gradient descent steps would converge in this case is still open. But yeah. I mean, with your landscape, after you do all the analysis, as long as we have some claims, some restrictions on the step size, it should converge, right?
You also need to make sure the feasible region is compact. Otherwise, it may diverge.
Yeah. So yeah, once we know, once we use your results and know the landscape, then we can maybe identify at least regions where it should converge with the right choices of the step sizes.
So the right choice of step size is tricky. So we don't know.
Sure. Like, yeah, exactly. So yeah. So at this set, you will see it's not so nice, this set. Yeah. Great.
Okay. Any other questions? Good. Thanks. Okay. If not, let's move on. So let's look at the first question: how does the feasible region look like? So first, we have a very simple observation. This set, of course, is non-empty, unbounded, and it can be non-convex. People know this, so it's just a simple observation. And here I give you a very simple example. So this is a scalar dynamic system. The state just a scalar, just one-dimensional system. And then if you write down the condition, basically means this matrix should be stable. And then you can direct check. You just look at two particular points. They stabilize the plant, so they are in this set. But if you take a convex combination and the resulting controller fails to stabilize the plant, and thus is not in the set. So the set of stabilized controller is non-convex. Very simple. This is a very simple example. And actually, our first main result is as follows. It's quite interesting. This set is not just non-convex. It can be disconnected. But the good news is that it has at most two connect components. So basically, this is one particular example. This is the feasible region of the set of stabilized controller is non-convex. For this case, it's connected. And for another example, it can be disconnected. And you may think about this kind of disconnectivity will bring some trouble for local search algorithms. Because if you begin with your iteration at one particular component, you may search around in this region. It's very hard to jump from one region to another region in general. So this actually is very different from the connectivity of static stabilizing state feedback controllers. And for this case, the set is always connected. But you may wonder, is this a negative result for local search algorithm based on gradient descent or some other variant? But actually, I'm going to tell you the answer, which is no. In this, the answer is not negative in this case, because we have shown that if the set has two connect components, then basically these two connect components are identical. So there is a smooth bijection between these two connect components. Basically, if you have one point in one component, and then you can build a map jumping into another component, and they are equivalent in terms of that the cost function is the same. So basically, there are some symmetry going on, even though we have a two connect component, but they are basically identical to each other in terms of the cost function. And actually, this bijection is defined by a similar transformation. If you know some control background, basically this corresponds to the change of controller state coordinates. Because the controller is a dynamic system, how do you change the coordinate for the controller may affect the realization of these three images. But from an input-output perspective, they are the same. So so basically, this is a good news. For a gradient-based local search algorithm, it actually makes no difference to search over either the connect component. So from the feed region perspective, this is good. So you can start from any where in the feed region and just search, and it will not cost you anything in terms of cost performance. So any question about this up to this?
Yes, could you briefly just explain more about why the existence of a smooth bijection makes the cost the same? I was kind of slow on that.
Yeah. So this bijection is defined by a similar transformation. So it's a control notion. So basically, if you have a dynamic system, the result is from here. So if you have a dynamic controller here, and then how do you choose the coordinate of this controller? We affect these three matrices, but it will not affect the input-output behavior. If you look at it from input, from output, or if you look at the dynamic system from a chance function or from the frequency domain, they are the same. But the realization of the dynamic system depends on how do you choose the coordinate of the controller. And basically, because input-output behavior are the same, then the cost will be the same. So basically, it just means this parameterization has a lot of redundancy. So it has some symmetry defined by a similar transformation. So it has a lot of redundancy. It's not kind of unique for a particular input-out behavior. Let's give us this smooth bijection. It is actually defined here.
I see. Okay. Thank you.
Okay. So actually, this kind of good news for the local search algorithm. Even though the set in non-convex can be disconnected, but it has at most two connect components, and you can search other component. It's fine in terms of cost function.
So sorry, yeah.
Yeah.
Depending on how kind of far away these two components are, this puts a requirement on the gradient step as well, right? In the sense that you want to make sure that your gradient descent is staying within one component, rather than jumping around, jumping between the two, in which case it might actually not converge. Is it is it possible that, for instance, you are in one component, you follow your gradient step, but you take a very long step size? You take a very long step, and then you go to the other component in which your cost actually increases.
It will not, because they are identical, so the cost will be the same. If you use this smooth projection, but I understand your question. So so actually, I'm going to talk about in the third part. You can make a known jump from one point to another point, which allows to escape some bad region by using some sort of transformation. So it's not like a general non-convex function. You know some structure property, and then from somewhere you can make a known step. You can jump from one region from another region, and in that case, actually we make progress. And of course, the key question: how do you make the jump? How do you make some criterion to say I'm going to jump from somewhere to another place? And actually, so this gives us a lot of opportunity. This smooth projection, similar transformation.
Yeah, but only when we know this structure, right?
Yeah, we only when we know the structure.
If we do blind gradient descent without choosing the right step size, it may break.
Right. Yeah. Right.
Great.
Yeah.
Thanks.
And furthermore, actually, we have some condition for connectivity. So we prove that the set is actually connected if there exists a reduced order stabilized controller. Basically, if you can find a controller with the internal state order less than the system state, then we can prove this full order controller will be connected. And this is a sufficient condition, and this condition becomes necessary if the plant is single input or single output. Basically, you only have a one-dimensional input or you only have one-dimensional output. And so that's how we find this example. Suppose your system is already stable in the beginning. You just want to improve the performance. Then we know you do nothing, will stabilize system. Your control can be take 0 to nothing. The system will be stable already. Then for this case, we already know the state of stabilized control is connected. So people know that a stable plant can be easier to control in some sense, and this result also support that effect. So if your system is stable in the beginning, then we know the set of stabilized control is connected. And here are two examples. The first example is open loop stable system. So here we have a stable system, and then you write out the condition, and you can plot the feedback region. This is how we found the example I showed you before. In this case, the set is non-convex but connected. Then if you look at a open loop unstable plant, this is a single input, single output. And you can also write down the stability criterion by looking at the eigenvalues. And then for this case, you have two connect components. Basically, one component where the parameter is positive, another component where the parameter is negative. And you will see they're almost identical. Just take a t equal to -1. So if you t equal to -1, you can jump from one component to another component. I'm going to talk quickly about how to prove this result. You may find actually this result can be difficult because the requirement is saying that this matrix to be stable, basically saying that the eigenvalue of this matrix have a negative real part. And the eigenvalue of a matrix can be very complicated to look at. And the proof of our result is using some classical result in control theory by looking at the Lyapunov theory. So I'm going to talk about this quickly in a high level. Hopefully you can get some idea how to prove this result. So let's look at the simple case, the static feedback case. So right now we only have one matrix to design. And again, the stage is similar. We want to make sure this matrix to be stable. The eigenvalue have a negative real part. And this is our set. And it is known that this condition is the same as a Lyapunov condition. So there exists a positive semi-definite matrix such as this product is negative definite. And now we look at here, we have two design parameters right now. So it's nonlinear and of course non-convex. And people know that you can do a change of variable. You can just say this product equal to another variable L, you do a change of variable. Once you do a change of variable, these two conditions become linear and they become convex. And all the non-convexity come from this non-linear change of variable. But fortunately, this non-linear change of variable is smooth. So basically, we can jump from a constant region to the set of stabilized controller, and the mapping is continuous and smooth. And then you will prove this set is connected, because this set is connected, and you have a smooth mapping, and the resulting set will be connected, but the possible non-convex. So this is a proof for the simple case. And for the general case of a dynamic controller, the proof idea actually is very similar, but we need to look at a more complicated Lyapunov condition. Now you see this matrix is called the Sam David, but now we have a block. So then if you do this multiplication, the result becomes much more complicated. And actually, back to like 30 years ago in the 1980s, people don't know how to do a change of variable to get a similar condition. And there's two results in earlier 90s, actually. You may consider there are reasons, because in control theory, it's very old. And there's a change of variable, which look very similar to this case, which allows us to make this set to be a complex set. And then there's a mapping from one from the change of variable to this control parameter. And the change of variable becomes more complicated. So I'm going to show you the change of variable, but it's kind of complicated. So the change of variable basically look at this. So there's a mapping from one domain to another domain, and then we'll get a two linear major inequality, and they are convex. And then there's a surjective mapping from this convex set to the set of stabilizing controller. And in this case, we need to use a set of inverted matrices to represent the similar transformation. And for this set, it can be disconnected. So the set of inverted matrices has two connect components, and that's why this set has at most two connect components. Because here this is connected, and this has two connect components, and this mapping is surjective, and then the resulting set has at most two connect components. And roughly, this is the proof of the main result. So any question about up to here?
Yeah, this is great. Is there any possibility that these change of variables can actually be generalized to more of a landscape analysis here instead of an algebraic trick? Can this be more general?
So actually, these two is very general. So this change of variable has been widely used in a lot of state feedback systems, and this is a standard for dynamic control. It can be used in like a lot of control design, like H2, H-infinite control, robust control, LQG. So I'm talking about LQG today. So it's not unique to LQG. It's kind of a general tactic for many dynamic control design. And actually, I think this is one of the breakthroughs in dynamic control design in the 90s. Before this paper, people don't know how to do this. Really, it's very complicated. I didn't know how they come up with this change of variable in the very beginning. But if you ask about like can we generalize this to nonlinear control, it can be complicated. I don't know how to do that easily, and maybe there are some similar procedure allowing us to use some change of variable to get a nice formulation for a particular control problem in a nonlinear case.
Yeah, thanks.
Okay, good. So we have talked about the first question about the feasible region of this non-convex optimization problem. So we know the set of the feasible region is not connected. But the good news is that it has at most two connect components, and they are equivalent in terms of the cost function, in terms of the input-output behavior of the controller. And then this is good news. And then the next question is that now we can search in this region, then we are fine. If we do the gradient descent, suppose we arrive at a station point, the gradient equals 0. Then how does this set look like? Are there like spurious station point? How do we check a station point is globally optimal? So this will be the next question I'm going to talk about. So again, we have some simple observation. This function, first of all, is a real analytic function over its domain. This is very smooth. You can take any derivative. It's infinitely differentiable. And this cost function has a non-unique, non-isolated global optimum. So again, this is the result of similar transformation. So once you have a global optimum point, suppose you have one global optimum point, AK, BK, CK, then you can introduce a class of optimum point. So basically, this define a class of optimum point, and in this case, all the points on this curve will be globally optimum. And basically, this function has a very rich symmetry structure defined by this similar transformation. This is a concept in control theory. Basically, it means if you look at the input-output behavior from the y of t to the u of t, they are the same, but it has different realization. So from the chance function perspective, they're the same, but from the state space realization, they are the same. And so for this cost function, it will have many station points, unlike the LQR, which only have a unique station point. Actually, this is a very important fact because once you reach the station point for LQR, and you are at the global optimum point. But this may not be the case for LQG because of this symmetry structure in this non-convex of formulation. So let's look at the gradient. So we can compute the gradient if we analytically, if we know the model by solving two Lyapunov equation. So this will be the gradient formula. And then our question is that suppose this gradient equals 0, then we can define a set of station points. And then how does this set look like? So we know this set is not unique and not isolated because we know the global optimal solution is not unique, not isolated. For this case, the gradient will be 0. And actually, we don't know whether there exists local minimal, local maximal set point or something else. So right now, I'm going to show you that there will be some set points, but right now we don't know whether there exists local minimum or it will not be local maximal, but we don't know this yet. So here I'm going to show you that for this class of cost function, there exists strict set point. For this, I'm going to show you a class of LQG problem for which we can show there exists set point. In particular, if you consider any open loop stable plant, then if we do nothing, basically the controller is 0. It's in the feasible region. And this feasible point is actually a station point. So we can prove the gradient for this particular controller is 0. And we can further prove that the corresponding Hessian is either indefinite or equal to 0. So indefinite means it's a strict set point. So basically, there's some direction with negative eigenvalue, then you can escape. But when the Hessian is 0, so basically around this region, the cost function will be very flat, and it can cause trouble for local study algorithm. You don't know where to go. So I'll show you one example for this case. Is again is a scalar dynamic, and then we can define the LQG using this cost function. And then for this particular controller, it will be a station point. And actually, for this simple case, we can compute the cost function analytically, and then we can compute the Hessian. And you will see for this Hessian, it's indefinite and has eigenvalue, has a negative eigenvalue and positive eigenvalue. So we can also find some other example for which the Hessian will be 0. So particularly for this case, at this point, the Hessian is exactly 0. So basically, for this point, it's very flat. If you do gradient search or local search, if you are with this region, you may have trouble how to move out this region quickly. So this is kind of some bad news. The set of staging point not unique, and actually the set of staging point have a strictly suboptimal point, had a strict set point. This is some sort of bad news, but we also have a good news. So all these kind of bad staging point correspond to non-minimal controller. If you look at here, this controller basically doing nothing. So it's not minimal. You are doing nothing. So it's not controllable. It's not observable. So we can also prove all these bad staging points correspond to non-minimal controller, correspond not controllable, not observable. And then we have another positive result, which is saying that if you are at a staging point plus some structural property saying that the point corresponds to a controllable and observable controller, then we can certify this point is globally optimal. So for this particular non-convex optimization, staging point is not enough to certify the global optimality, but we can have some other structure property saying that the point corresponds to controllable or observable controller, then we can prove it's globally optimal. So basically, given a any staging point, if this staging point corresponds to a minimal controller, then it's global optimal. And of course, this set of all the global optimal controller forms a manifold with two connected components, and they are connected by a similar transformation. So this is the positive result. And I'll show it to you another, again the example of single input, single output system. And for this case, all the set of global optimal controller look like here. And for this case, this all set of global optimal controller look like here. So if you are in a staging point, if you can certify the staging point corresponds to a minimal controller, then you are good. So the proof of our result actually is not new. You can consider it as a special case of a old result. So basically, we prove if you are at a staging point, if the staging point corresponds to a minimal controller, then we show that all these staging points are in this form. And basically, this is the form in the Ricardo equation. So you can solve the Ricardo equation, and this is the common feedback gain, and this is the LQR feedback gain. So we know this is global optimal, and we prove that all the staging points that are minimal are in this form, and basically they are globally optimal. So basically, we again use the classical result saying that we know the optimal solution comes from the Ricardo equation. Then we prove the structure of this staging point have this exactly same form. Then it's globally optimal. And the proof actually just follows the derivation. It's kind of complicated. We just show that once you make this to be 0, then you can solve it. You can find it, and then you can show they are in the form of a Ricardo equation. And the derivation is kind of complicated. You need to do a lot of calculation to prove this. But actually, this result is kind of not new. You can find similar result in like almost 40 years ago. Okay, so this is a good result, and it has some good implication. So if you do gradient descent, suppose you converge, and then suppose you are in a minimal controller, then we arrive at the global optimum. So this is a very simple corollary, and we show some numeric example for some other system. We indeed observe good convergence, global convergence. But of course, there are a lot of open questions, because first of all, how do we choose step set? How do we guarantee it converges? And we also know there are some set points. Basically, it may converge to set point, and then how do we escape set point, and what is the convergence speed, and all these three kind of open, and also right now we use this standard state space parameterization, and maybe there are some other parameterization for this LQG problem, and which may give us some better landscape property. Okay, I'll stop here for 1 second if you have questions.
So, in principle, my hashing in this case, I can write it down fully symbolically, right? I mean,
you can write down symbolically, but
yeah.
it will be very complicated.
So then it's yeah, and then if I think about its characteristic polynomial, so basically I have a huge multivariate polynomial, and I want to understand the
it will be a rational function, so it's a ratio of two polynomials. It's not just a polynomial.
Right. And so yeah, so basically I'm thinking about some symbolic computation kind of algorithms, which you know, there's cylindrical decomposition algorithms that in principle you can take multivariate polynomial and kind of understand as different components of well, different components in the landscape with the same sign for each dimension and all that. But it's a doubly exponential algorithm to you know, in the simplest case. So yeah, I'm just thinking, you know, in principle there is something, but we probably cannot do it easily.
Yeah, it's interesting question. So for simple case, like for the example I show you here, yeah, we can compute it for particular point, the hashing. There will be some expression. We know how to compute it, but the expression can be very complicated. So I don't know how to directly look at the expression then to come up with some else.
It's where some okay. It's very interesting to me because some of the symbolic algorithms that I gave up on might actually be useful in this case.
Yeah, I'm very happy to talk about this later on. Yeah, it's kind of interesting question. So let's move on. So this is a good result, and I have a good implication. So let's give a comparison with the LQR, the state feedback case. So both of them can be formulated into a optimization form as this. And then for the LQR, we know the set is always connected, and we know stage point is actually unique. So once you arrive at a stage point, you are getting the global optimal solution. And furthermore, this cost function satisfies property of gradient dominance, and indeed there's a condition for step size, and you can get globally fast convergence. And this function almost like a strict convex function. And for the LQG case, this set first of all can be disconnected, but it has at most two connect components, and they are almost identical to each other. And it has non-unique, non-isolated station point, and it also has strict set point, which is strictly suboptimal. But we also prove that all the minimal station points are global optimal. This kind of good news. And right now we don't know the convergence speed or the convergence condition, how to choose the step size, and there are also some other open questions. And for the LQR, there are a lot of papers in the past few years because people want to understand how like the power acceleration algorithm work on standard control problem. And for LQG, there are only very few papers, and I think our paper is one of the first. And if you're interested, you can take a look at the report here. Okay, good. I think we have a few other minutes. I can talk about how to escape some bad set points. So we know there are some set points in this LQG formulation, and how we can escape this set point by doing some perturbation, by doing some non-step jump. So first of all, let's look at a general geometry of a function 5x. So if we are at a stage point or a critical point, which means the gradient equal to 0, it can be a minimizer. It can be a setter point. It can be a maximizer. And we know in LQG, this may happen. So the setter point is called strict if the Hessian has a strict negative eigenvalue. Basically, you have some direction, like say this direction. You can do a perturbation that you can escape. If the Hessian is 0, or the minimum eigenvalue is 0, or it's only probably semi-definite, and then this is called a high order setter point. So basically, there's no such escaping direction, and this can be tricky to work with for general non-convex function. And actually, people know that for this class of setter point, a simple perturbed gradient descent can escape very efficiently. And you can take this paper. It can become very popular. You can do perturbed gradient descent to escape some strict setter point. But for LQG problem, we show that there's some high order setter point with 0 hash, and this strategy may not work. So you may need to do something further to escape this kind of a setter point. And our idea is that in addition to the standard perturbed gradient descent, we do some structural perturbation. It's kind of the similar transformation we do. We jump from one point to another point, and this jump is based on a similar transformation. So basically, we can jump from a high order setter point to a strict setter point with the same LQG cost, and this is performed by doing some transformation, doing some similar transformation. So this is a high-level idea, and this procedure is possible because of the following two results. So first of all, we know that all the bad staging points are non-minimal. So there's uncontrollable or unobservable mode in the system. And furthermore, we prove that all the bad staging points are in the same form, in the sense of that if this is a staging point but not minimal, then we can take a minimal realization, and this will be a staging point as well. And they have the same LQG cost. So basically, you can jump from a staging point to a staging point in this form, and there are some zeros. This is basically the uncontrollable, unobservable mode. And this block you can choose randomly. You can choose to be any stable block. And second, we prove that if you choose this block randomly, and the resulting point will be a strict setter point with probability almost 1. So almost 1. So there's a technical condition to guarantee this will be a strict setter point. So basically, you can always do this. You can start from a staging point, do a minimal realization, and you go to this form, and you choose this block randomly. So basically, you do a random structure perturbation of the point, and you are guaranteed to be at a strict set point. And then you can apply the perturbed gradient descent. And basically, there are some technical conditions. If you are interested, you can take a look at our paper. And right now, suppose we do this perturbed first, and then we are at a strict set point. Then we can apply the standard perturbed gradient descent. So basically, we combine a structure perturbation in the LQG problem with some sort of standard perturbed gradient descent. Then we can escape these quickly. And here I show you one example. This is a particular LQG problem. If you do the standard gradient descent, you will be stuck in this region. The cost will not jump, will not decrease, and you will do a lot of iteration. And then if you do standard perturbed descent, you may go away, but you take some iteration, about 1,000 iteration. But if you do our algorithm, we first do a perturbation first, and you can escape this very quickly. So this is a new perturbed gradient descent to escape some high order setter point. Okay, great. Now the conclusion. So we looked at the non-convex optimization for LQG control, and we show that these landscapes are much richer and much more complicated than LQR. And then the field region can be disconnected, but has at most 2 connected components. And we also show the minimal state point are globe optimal, and we show a new perturbed gradient descent algorithm to escape some class of high order set points. And there are some other open questions. The first question, how to certify the optimality of a non-minimal staging point? We know the minimal staging point is globe optimal, but how to certify the optimality of a non-minimal staging point, and how to give a proof of convergence of the perturbed gradient descent, and more quantitative analysis of a PhD algorithm is also required. And you may also look some other model-free parameterization, and which may give some better landscape. So yeah, that's it. Thank you. I'm happy for questions.
Thank you so much. Really clear talk. It's basically a perfect talk. Thanks. Questions, Arya? Are you?
I'm just I have something, but if like I have some peripherally related question, but maybe if there is some better, more related questions from others in the audience.
Any question from others? We're kind of running out of time anyway, so. Arya, do you want to ask anything?
Yeah, I had some question about this. So at the end, you basically said that if you can find any minimal stationary point, any minimal stationary, any minimal controller, then that's going to be a globally optimal controller. So that's very much like, very like nice non-convex optimization problems like PCA and others, where you do not have you have this nice landscape. So here, what exactly was the reason? And I sort of missed that, perhaps. That what?
Yeah, so it's kind of not so obvious. So because come from the proof. So basically, if you are at the station point, so you will have a set of algebraic equation. Okay, you will have a set of algebraic equation, and if you assume the controller is minimal, so you have some controllability, observability of the point, and actually you can take the inverse of something. So you can define a similar transmission, and then you take the inverse. Basically, some matrix become invertible, and then you can actually solve this point, and you show this point actually come from the Descartes equation. And so we know the Descartes equation give us global optimal solution from the classical result.
Yes.
And then this will be global optimal. So actually, this is not a direct proof. It's kind of a circumvent. We know the optimal solution comes from the Descartes equation. Then we prove the station point plus minimal controller will be in the form of a Descartes equations. Then we prove the global optimal. So it's not a direct proof. Actually, direct proof can be very complicated. Even for the Descartes equation, why the Descartes equation give us global optimal controller, there's some proof behind it. So
I see. Okay, very nice, very interesting work.
Yeah, actually, so in some sense, our work is motivated by the work on PCA from the matrix factorization, and there are some results which say, okay, you have some net structure of a landscape, and that's why I want to look at for this control problem. And actually, the control problem is kind of more complicated than in some ways than the problem, because of this matrix inverse and something.
One other thing is like, how robust is the gradient descent algorithm in this context? I mean, can you have noise in the system, or you can have other type of corruption like quantization or something, and it will still give you something reasonable?
So a force direct result, we don't know, but people do this a lot in dynamic. People do this recently, so they just apply like model-free process iteration to some control problem, and they observe some good performance. And we want to analyze some theoretical reason behind it. And right now, this is just the beginning of this investigation, and we don't know whether like if you have a corruption with the gradient descent, how the convergence, and even you have perfect gradient information, the convergence is not very clear yet. How to choose the step size, which point where it converges to, and what's convergence speed.
So it is very, very, very sensitive to the step size, if not anything else. Okay.
Yeah, but at least knowing the landscape to some extent significantly helps with that next step of analyzing the behavior of the algorithm on this landscape.
Yeah, I think that's all I had to ask.
Okay, thank you.
So we